All right, one thing about this is that we often have magnetic fields that we have to show in 3 dimensions. You'll see why really shortly, but we often have magnetic fields that go into or out of the page, which we've never really dealt with before. Normally when we showed fields before, they were kind of doing this, or they were doing something like this. But now we're going to have 3-dimensional fields. So if they are going out of the page, it's going to look like a bunch of dots. That's it. I'll show you in class, but it's basically like the point of an arrow coming right towards your face. If the field goes into the page, then you get these X's, which is supposed to be the butt of the arrow pointing up towards your face. Okay, a magnetic field is going to exert a force on a moving electric charge. If you have just an electron hanging out, you can put the strongest magnetic field in the world around it. And if that electron is not moving, no magnetic force will occur. If, however, the electron starts moving, you will suddenly get a magnetic force acting on it. So it requires motion. It's strange. It's different than other things like gravity or electrostatic force, which will just act between things that aren't moving. This one requires the little particle to be on the move for it to work. Also really weird with magnetic force is the direction the object is moving, the little particle is moving, actually influences how much force it feels. Just because you're moving doesn't even mean you're going to necessarily have magnetic force acting on you. The direction really matters. Let's take a look at the equation. So Q, as you know, is the charge. V is the speed of the particle. Okay. And of course that's measured in meters per second. B, which you know from level 1, is the magnetic field strength. And as you know from level 1 and understand it, it's measured in Teslas. So that leaves us with the sine of theta thing. And that's where this direction comes into play. Here is a magnetic field, okay, going off to the right. If we had an electron in here, actually let's make it a positive charge just to make this easier at first, and it's bombing along in the same direction as the magnetic field, it would actually not feel the force. Okay, here's why. F is equal to QVB sine of theta. Well, theta is the angle between the magnetic field lines, the direction of the magnetic field, and the direction that the little particle is moving. So in this situation, that angle is 0. They're both going the same direction. And sine of 0 is 0, so you would have no force. The same thing happens if the particle is moving the opposite direction. Since F, Q, V, B, sine of 180 degrees, because the angle between this would be 180 degrees, sine of 180 is 0, so the force is 0. So when would a particle feel the most magnetic force in a field? Well, let's go back to our original situation, and let's look at our equation. F equals QVB sine of theta. Okay, well, what would make sine be the largest? If you remember from math, sine becomes the largest when we're at 90 degrees. In other words, perpendicularly. So if you had 3 electrons, okay, or I'm sorry, let's do positive charges. Okay, so one's going this way, one is going this way, and one is going this way, and they're in the same magnetic field, they have the same charge, and they're going the same speed. That would mean this guy would feel nothing, this guy would feel some, okay, and this guy would feel the most. And now we get into the very interesting question of which direction that little particle would feel a force, okay? Because we've talked about that equation and how much it would feel. We haven't talked about which way it would feel the force. So let's say we have a little positive charge bombing into a magnetic field here with a certain velocity. We know that it will feel a force, and we can calculate how much of a force it's going to feel using F is equal to QVB sine of theta. But which way is it going? In order to do that, we are going to have to use something that is near and dear to all physics people, which is the right-hand rule. Engineers, physicists, any kind of hard scientist is going to end up using the right-hand rule at some point, and a lot of us use it a ton. So welcome, this is very exciting. I'm so thrilled to initiate you into our little handshake here. Okay, so here we have my right hand. I know it's stunning. I will be soon quitting teaching to become a famous hand model. Let's talk about how we're going to be looking at this, okay? So remember the equation, F is equal to QVB sine of theta, okay? Well, if we want to find which direction the force is, we're going to look at the direction the velocity of the particle is and the direction of the magnetic field. If you notice, this almost looks like the X, Y, and Z of a coordinate plane. This is the finger that you are going to point in the direction of the velocity the particle is going, so the thumb, okay? This one is going to point in the direction the magnetic field is pointing, and this guy is going to tell you which way the force will be. A few things when you're using the right-hand rule. Make your fingers be at right angles to each other, and don't get sloppy. Don't let them sort of bend together. Otherwise, you're going to get very confused really quickly. So make it look like an L between each of them. So you see an L, an L, an L, okay? Okay, so once again, we're going to have our magnetic field, which is pointing into the page, and we know that by the X's. We're going to have a positive charge going in, and we're going to try and figure out which direction is going to feel force. Okay, you're going to go finger by finger. So first you're going to take your thumb, and you're going to point it in the direction that the particle is moving. So your thumb should be pointing this away. Okay? All right. Next, and there's pretty much no way for me to draw this well because I'm not that great of an artist, but I'll give it a shot. You're going to take your pointer finger and you're going to point it in the direction that the magnetic field is going, which in this case is into the page. So now I will botch that image. Okay, I decided I can't actually draw that. So now you got a picture of me with my fingers looking like I'm flipping you off. So once again, we have our particle going this way, so that's the V. The magnetic field is going into the page, so you're pointing your finger straight down into the page, okay? And the third finger is actually going to show us the direction of that force. Okay, so this guy would feel a force up toward the top of the page. Okay. Let's try that again. So now we have a positive charge going down. We have a magnetic field coming out of the page, and we know that because we're using dots. In other words, we're imagining arrows sort of shooting out straight at our face. So which way would this guy feel a force? You can pause the video right now if you want to try it on your own. So your hand should have looked like this. Okay, so here is a nice picture of my hand. Look how nice Shannon's boots are. Okay, so we got the magnetic field is, well, let's actually do the velocity first. So this is the direction that the particle is going. So that's the V. Put that like this, okay? And the magnetic field is pointing out of the page. So it's coming like straight at you, just like my finger is right here. And that means that the force finger is pointing this way. So this guy, when he gets in here, is going to feel a force to the right. Notice that for all of this stuff, I have been using my right hand so far, okay? And that's because you use your right hand for positive charges, and you're going to use your left hand for negative charges. You will probably forget this at some point, and then you will cry bitter, bitter, sad tears, okay? So try to remember it. If you really need to, I would suggest a fashionable tattoo like this, and then people will really know that you're super into science. Okay, let's have a dance party now. Right hand roll.